Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sigma and the pi bond, and these bonds are the two types of covalent bond. In the previous lecture, we have talked about the orbital concept of the formation of the covalent bond. Now, let me recapitulate that thing. When the two atomic orbitals of different elements containing one electron each but with opposite spin overlaps with each other, then the formation of covalent bond takes place. The two electrons with opposite spin actually comes in that overlapped region of the two atomic orbitals. That's why the formation of covalent bond is taking place. Today we are going to talk about the two types, the sigma and the pi bond, which is dependent on the position of that overlapped region with respect to internuclear axis of the two atomic orbitals. So let us discuss this thing. The two types of covalent bonds, that's sigma and the pi bond. I'm writing sigma bond over here and pi bond over here. Now what is sigma bond? It is the bond formed when there is head-on overlap of atomic orbitals that is the overlapped region between two atomic orbitals are on internuclear axis. The axis which is passing through both the nucleus is called internuclear axis, and the overlapped region of atomic orbital is present on internuclear axis. On internuclear axis. So let us understand this thing first. The sigma bond has a symbol like this. This is the sigma bond. Now we are having three types of sigma bond. The first one is sigma S and the S. This is the nucleus and this is the spherical s orbital. This is the another nucleus and this is the another s orbital. During the covalent bond formation, these two atomic orbitals will come closer to each other and they will be the overlapping between the two atomic orbitals. So it's gonna form the nucleus and the nucleus. This is the s orbital of the first atom. This is the s orbital of the second atom. Now let me draw the internuclear axis, the axis which is passing through both the nucleus. So this is the internuclear axis. Now just observe that the overlapped region, this is the overlapped region, the overlapped region is present on internuclear axis. That's why it's a sigma bond, the sigma bond between s orbital and the s orbital. That's why it's called a sigma ss. Now let's talk about the second type of sigma bond. The second type of sigma bond is sigma S and the P. So this is the nucleus and this is the S orbital of the first atom. Now this is the nucleus and this is the p orbital of the second atom. Now for the covalent bond formation, both the atomic orbitals will approach each other. Now what's gonna happen? This is the nucleus of the first atom and that's the s orbital, and this is the nucleus of the second atom and this is the p orbital which has overlapped with the s orbital of the first atom. Now let me draw the internuclear axis, the axis which is passing through both the nucleus. So this is my internuclear axis over here. This is the internuclear axis, and here you can see that again that overlapped region is on the internuclear axis. So that's why it's a sigma bond, and this between the s orbital and the p orbital, so it's a sigma s and the p. Now let's talk about the third type of sigma bond. The third type of sigma bond is sigma p and the p. Now this is the nucleus of the first atom and that's the p orbital, the dumbbell shape p orbital. This is the nucleus of the another atom and this is again the dumbbell shaped p orbital of the another element. Now again for the covalent bond formation, both the orbitals will approach each other for overlapping. So that's the nucleus. Now that's the p orbital of the first element. Now it's the nucleus. Now it's the p orbital of the second element. Now let me again draw the internuclear axis. So this is the internuclear axis which is passing through both the nucleus. The nucleus is over here and the here. Now here again you can observe that the overlapped region is on the internuclear axis. So that's the sigma bond formed between the p orbital and the p orbital. So that's all about the sigma bonds, and here you can see that the sigma bond is formed by the head-on overlap of the atomic orbitals and the overlapped region is on the internuclear axis. That's why we are calling it a sigma bond. Now the overlapping efficiency is greater in sigma bonds, so that's why sigma bonds are also a strong bonds. Now let's talk about the pi bonds. Sorry. Now let's talk about the pi bonds. What are pi bonds? It is a bond formed when there is sidewise or the lateral overlap of the atomic orbitals and the overlapped region is perpendicular to the internuclear axis. So I am writing, it is the bond formed by the sidewise or we can say lateral overlapping of the atomic orbitals and the overlapped region is perpendicular to the internuclear axis. Now, some very important points about the pi bond. First of all, the sidewise overlap or the lateral overlap is possible only in p orbitals. I'm writing lateral overlapping, or we can say sidewise overlapping, is possible only in p orbitals. Now, the lateral overlapping is possible only in the p orbitals. We know that p orbitals are actually 3 in number. There are actually 3 orbitals in p subshell, and they are px, py, and pz. Now, for the formation of pi bond, there must be one sigma bond in the 3 orbitals, and it's a very important point. That means out of the 3 orbitals of the p subshell, one must form sigma bond, only then other 2 will form the pi bonds. I am writing out of 3 p orbitals, comma, one of them must form one sigma bond, only then other 2 orbitals will form pi bonds. Now, let me show you the rough diagram of the pi bond formation. The pi bond is always formed between the p and the p orbitals of the 2 elements. Now, let me show you how is sidewise or lateral overlap is formed, which is perpendicular to the internuclear axis. This is the nucleus of the first element, and that's the p orbital of the first element. Now, this is the nucleus of the second element, and that's the p orbital of the second element. Now, what's going to happen? There will be the sidewise overlap. How? That's the p orbital of the first element, and now this is the p orbital of the second element, and here you can easily observe the sidewise overlap. Now, let me draw the internuclear axis. This is the internuclear axis. Now, let's talk about the overlapped region. This is the overlapped region for the p orbitals for the sidewise overlapping. Here you can easily observe that the overlapped region, let me take a different color, you can easily observe that overlapped region is perpendicular to the internuclear axis, Now let me draw it again. The overlapped region is perpendicular to the internuclear axis. You can observe it very easily. Now, this is a sidewise overlap of two p orbitals in which the overlapped region is perpendicular to the internuclear axis. So that's why it's a pi bond. Now let's come to the point. The p orbitals are 3 in number, that's px, py and the pz. Now out of the 3 p orbitals, one of them must form one sigma bond, only then the other 2 orbitals will form the pi bonds. Now let's understand this point. I hope you understood the basic structure of pi bond. Now I'm moving to the next point from here. Now I am drawing 3 p orbitals simultaneously. You have to just imagine this diagram in 3 dimensions. Here first of all, this is pz. I'm marking this to be pz but not the x. I'm taking it to be pz, and that's the pz of the second element. Now I'm taking the py, that's the py of the first element, and that's the py of the second element. Now that's px of the first element, the blue color, and that's the px of the another element or the second element. That's the py. Now there will be the sigma bond formation between the pz and the pz. Let me show you. So first of all, this is the internuclear axis and the overlapped region is on the internuclear axis. So that means we got the sigma bond between the pz and the pz. Now firstly, the formation of sigma bond will take place between the two p orbitals. Now the other two orbitals, the px and py, are eligible for the pi bond formation, but firstly sigma bond has to be take place. The sigma bond formation has to be take place. Now let's talk about the pi bond. Now this is the py and this is the another py. Here I am showing you the overlapping with this pen, and here actually I can't show the diagram like this because of the space problem, so I am showing it like sidewise overlap to be like this. This is the pi bond, the side overlap, and this is again the pi bond. Sorry, these two interactions will form one pi bond, and please do clear this thing in mind. I'm drawing it again. Obviously, when both the lobes will overlap with each other, then the formation of one pi bond will take place. Don't get confused that there are two pi bonds. It's actually one. This is the upper lobe overlapping. This is the lower lobe overlapping, and it's the formation of one pi bond. Please don't consider it to be the two pi bonds. This is the overlapping of the upper lobes and the lower lobes. When the overlapping of both the lobes, the upper and the lower, take place, then the formation of one one pi bond will take place. I'm repeating it again. When the overlapping of both the lobes, the upper one and lower one, will take place, then the formation of one pi bond will take place. Now, let's talk about the third one, the px. Now, here, this is the px, and this is the px. Just imagine it in 3 dimensions. Now, both the lobes, the upper one and the lower one, will overlap with each other. Then the formation of another one pi bond will take place. So, just imagine it in 3 dimensions. The first overlap and the second overlap. Now, both the overlaps will make one pi bond. So, I hope you all understood this thing. Firstly, there will be the formation of one sigma bond between the firstly there will be a formation of one sigma bond by the one p orbital. Only then the formation of pi bond is possible for the another p orbitals by sidewise overlapping. And I'm repeating it again and again. In the pi bond formation, both the lobes will overlap, the upper one and the lower one, and will be considered as one pi bond, not the two. Please always keep this thing in mind. So here we got the one sigma bond. Let me take an example. It's an example of let me take an example. It's an example of N2 actually. So we know that nitrogen and nitrogen will have triple bond, out of which the one is the sigma bond and the another two will be the pi bond. The pi bond and the pi bond. So in case of triple bond, we have one sigma and the 2 pi. I am writing in case of triple bond, we have always one sigma and the 2 pi bonds. Let me take an example of double bond. Let's talk about the O2. Now, oxygen and the oxygen. In oxygen and oxygen, we have one sigma bond and the one pi bond. And the last p orbital is actually completely filled in the oxygen. It's 2p4. So out of 2p4, the 2 electrons will be in the one orbital. So that orbital is completed by the 2 electrons. So that means the 2p orbitals will be engaged in forming the 2 bonds, out of which the one will be sigma and the another will be the pi. And in case of single bond, it's always a sigma. I'm writing in case of double bonds, comma, we always have one sigma and the one pi bond. And in case of single bonds, comma, bond will always be sigma by head-on overlap or the overlapped region on the internuclear axis. Bond will always be sigma bond. So very first condition for the formation of pi bond, that there must be one sigma bond. Only then the formation of pi bond will take place. And let's come over here. The overlapping of the two lobes, the upper lobe and the lower lobe, will give rise to one pi bond. Let me write this thing also. The overlapping of both the lobes of one orbital, that is upper lobe and the lower lobe, will give rise to one pi bond. Here what I'm telling about, that you can see the overlapped region which have been marked by the yellow. The overlapped region or the overlapping of both the lobes of one p orbital, that is the upper lobe is this one, and the lower lobe. The overlapping of both lobes, the upper one and the lower one, will give rise to only one pi bond, not the two. I am clearing it again and again. Please don't get confused, that the overlapping of both the lobes, the upper one and the lower one, will give rise to one pi bond. So that's all for today. I hope you all understood today's lecture, in which the sigma bond is very much clear, that head-on overlap or when the overlapped region is on the internuclear axis will give rise to a sigma bond. But for the formation of pi bond, we have one condition, that there must be at least one sigma bond for the formation of the pi bond. So pi bond is always formed mostly between the p orbitals, and we know that p orbitals are 3 in number: px, py and pz. Out of these 3, the one must form sigma bond, only then the other two will form the pi bonds. And another important thing which I have written over here, that the overlapping of both the lobes of one orbitals, that's the upper lobe and the lower lobe, will give rise to one pi bond, not the two. And here the students get always confused, and I'm clearing it again and again, that the overlapping of both the lobes, the upper lobe and the lower lobe, will give rise to one pi bond. So that's the three-dimensional diagram for the formation of one sigma and the two pi bonds. Here the sigma bond has been formed by pz and pz. After that, two pi bonds have been formed. The one pi bond between py and the py, and the another pi bond between the px and the px. So that's all for today. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.